Hi, I'm Enayat Ullah and I'll be talking about machine learning via algorithmic stability. This is joint work with Tung, Anup, Ryan, Rossi, and Raman, Arora. The basic unlearning problem is as follows. We have some machine learning task and a given dataset S. We apply some accurate algorithm A to get A of S. We then get a request to delete some point Z which was present in the dataset. We now apply algorithm U, which takes A of S and Z, and we want its output to be approximately equal to what we would have obtained had we applied A to the dataset without the point Z. Note that there's a trivial solution, which is to recompute, but often this is computationally expensive, and the main objective is to do better. The motivation for this problem is privacy laws. Currently, a lot of services and analysis is user data driven, like recommendation systems. This has resulted in regulatory bodies enacting laws which aim to empower users with more control over their data. In particular, European Union GDPR is one such regulation. The articles shown at a high level say that a user can request to have their data deleted, and there are other such laws. But what does it mean to delete data or to unlearn? In particular, what is the appropriate notion of approximation here? There are many considered in the literature. We instead use the strictest notion, which we called exact unlearning. As the name suggests, we want these quantities to be equal. For randomized algorithms, which will be the case for us, this is equality of probability distributions. We now come to the problem setup. We consider the standard setup of empirical risk minimization. Herein, the goal is to find a model which minimizes the training loss, which is the average loss over data points. Here, W is the model and Zi's are the data points. We assume that the loss is smooth Lipschitz convex, and the parameter vector W is d-dimensional. This class of problems captures many machine learning problems like linear and logistic regression. Finally, instead of an isolated deletion request, we consider a stream of deletions as well as insertions. So we start with a data set of endpoints, apply algorithm A, which outputs a model and perhaps some metadata. We get an edit request, we update both using U, and this goes on. Our main result is the following. We give algorithms AU such that for any Lipschitz smooth convex F stream of edits and a parameter O, it satisfies exact unlearning at every point in the stream. Its accuracy at every point in the stream, measured in excess empirical risk, is bounded by some quantity which I'll come back to. The expected total unlearning time is rho times k times training time for k requests. Rho here is an external parameter which controls the trade-off between accuracy and unlearning time. Note that the unlearning time is stated as if the algorithm recomputes rho fraction of time. This is indeed the nature of our methods. The accuracy is minimum of two quantities. For high dimensions, the accuracy behaves as 1 over square root rho n, whereas for low dimensions, the minimum is the second term. The result is a strict improvement over recomputation in the low accuracy regime. What I mean is, suppose we fix an accuracy alpha greater than the quantity shown, then there exists a row smaller than 1, which we can use to instantiate the above result, and then the unlearning time will be smaller than the recomputation time. This low accuracy regime is particularly interesting for machine learning purposes, where the goal really is to minimize the population risk. Our results extend to non-convex optimization. Moreover, in some cases, the training algorithm is differentially private. We will now give an overview of key ideas and techniques. The main idea is the notion of algorithmic stability, which we call total variation stability. We say that an algorithm is so TV stable if for all data sets differing in one sample, the total variation distance between the algorithm's outputs on those data sets is at most rho. The motivation for the above is the maximal coupling characterization of total variation distance. Total variation distance can be defined as the minimum expected disagreement of samples drawn over all couplings of P and Q. A coupling achieving the minimum is called a maximal coupling. When sampled from a maximal coupling, we have that only TV fraction of samples differ. The way we use the above ideas is by designing a TV stable algorithm. What we propose is based on a variant of gradient descent, and then a corresponding unlearning algorithm. This constructs a coupling. This should be efficient, that is, it should be faster than recomputation, and near maximal, so it recomputes only a few times. This is achieved by rejection sampling and reflection coupling techniques. Thank you.